Okay, so I'm going to go over one of the most important continuous probability distributions, which is the normal distribution. Okay, the normal distribution sort of arises in many settings or in many situations involving measurement. Okay, examples include, we can model, for example, the distribution of people's height with the normal distribution. After, say, we account for differences such as male and female, once those are taken into account, then we generally find a pretty good model of people's heights given by this distribution. Okay. Also, the relative change, so not the absolute change, but the relative change, so from one day to the next, okay, how much you multiply the price by in a stock index is often modelled by a normal distribution. Okay, measurement of many physical phenomenon. Okay, for example, the normal distribution was first discovered by Carl Friedrich Gauss, who's a famous mathematician, and it's also sometimes called the Gaussian distribution, and he used this to track the path of certain comets travelling through our solar system. Okay, results of referendum polls, results of polls for elections, often modelled using a normal distribution. So, like if you did a kind of Brexit referendum poll, you would have been using a normal distribution. So Gallup or someone like this would have been using normal distributions all the time. Okay. Also, things like the distribution of, say, heat. So if I applied a heat source to a metal bar, for example, at a certain point, and looked at the distribution of heat as it evolves over time, it would look like this distribution, a normal distribution. Also, the same happens for if I had a quantum particle undergoing no force, then the distribution of where it should rise should be also given by this kind of normal distribution. So it's something that occurs all the time. Okay, so arguably, you could say that the normal distribution is perhaps the most important probability distribution. Okay, so one could debate whether there's such a thing as the most important probability distribution, of course, but certainly if there's going to be a number one candidate, or if there's going to be a sort of top candidate, probably for most people it's going to be the normal distribution. Okay, so why is this? So why does it occur in so many settings, and why do I think it's, and other people think it's one of the most, if not the most important probability distributions? Well, roughly because it's the distribution that arises when you add up lots of small, and I'll put in brackets, independent errors. Okay, so like for example, if we look at somebody's height, okay, there's lots, after we sort of taken account for the big genetic difference of being male or female, okay, there's lots of little small factors around your diet, around your lifestyle when you're growing up, around small genetic variations in each person, which are all small contributing factors to what ultimately lends to being your height, okay, and these all add up cumulatively, okay, to give a distribution. When the distribution that arises from adding up lots of small errors is a normal distribution, and that's why it's a good model for height, for example. Okay, so this notion, okay, of adding up small errors and it going to normal distribution is called the central limit theorem. Okay, so I'll discuss that in a minute. Okay, but first I guess I should actually describe what this distribution is. Okay, so we'll talk about what normal distributions are, and then I'll discuss a little bit about the central limit theorem. Okay. Okay, so the definition of what I'll call a standard normal distribution . Okay, with the following. So the standard normal distribution is the distribution with probability mass function probability density function as follows. So phi of x, normally we've used f, but in this case we're going to use phi. We use slightly different letters normally when we refer to a normal distribution, which is equal to e to the minus x squared, okay, and then we're going to divide this by 2. And then we need to apply appropriate normalizing constant to this guy. So this is all the things that are to do with the value of x. And it turns out the thing that normalizes this distribution to 1, so the integral of phi is 1, is 1 over square root of 2 pi. Okay? And the range of this distribution, okay, is from minus infinity to infinity. Okay? So let's just do take a quick look at what this distribution actually looks like. Okay, so I'm just going to go over here, right, and I've prepared a little program here that imports a library that does some numerics, imports some things for plotting, and then I'm going to grab a binomial distribution and a normal distribution here. And what I'm doing here is plotting between the values of -4 and a 4, 100 points which have the appropriate density, probability density of a normal distribution. Okay, so let's just grab that. Okay, we'll just give it a second. This is essentially what a normal distribution looks like. Okay, so it's got this kind of nice curved kind of bell shape. Okay, we see quite a lot of the density is really focused between, say, values of say -4 and 4, and some people would even say between -3 and 3. Okay, so we can actually do, I'll just quickly show you, but we can actually do some calculations for the ranges So I can calculate, for example, the amount of probability between, say, -1 and 1 by taking the cumulative distribution function which for the value of 1, which gives me everything, all the area to this side, and then minusing off the area from -1 onwards. And that'll give me the amount of the distribution here that's between -1 and 1, and that's what this is doing for me here. Okay, so we see about sort of 70% of this distribution, 68.2%, lies between here and here. Okay, then next if we look between -2 and 2, okay, then we see that we get about sort of 95% of the probability between -2 and 2, and then finally between 3 standard deviations we're getting really most of the probability, say 99.7% of the probabilities between -3 and 3. Okay, so that gives you an idea of sort of how quickly this distribution is going down to 0. Okay, so it goes down very tightly to 0 at its tails here, because e to the -x is a very fast decaying function. Alright? Okay, so that gives you a bit of an idea what a normal distribution looks like. Alright? So, 2 facts about a normal distribution is that, and I'll show maybe later, maybe not in this video, but it can be shown that a standard, and I'll write STD to mean standard here, normal distribution has mean 0 and variance 1. Okay, so it's not that surprising that the mean is equal to 0. Notice that the function is nice and symmetric at either side of 0, so the average is going to hit at 0 as well. Alright, showing that the variance is equal to 1 is actually a bit tougher and involves a kind of nice trick which I won't present now, but we'll do maybe in a later video. Alright, when Z is a standard normal distribution, is a standard normal random variable, we write Z is given by this n, and then 0 and 1. 0 gives the value of the mean, the 1 gives the value of the variance. Okay, and I'll note that quite often we use Z for normal random variables. Don't have to, but quite often, particularly standard normal random variable is denoted by capital Z. All right. Once again, that's a convention. It's not something that you have to do. You can call it whatever you like. All right. Okay. The cumulative distribution function is then given by, we often use the notation phi, so we're using capital F before, but for normals we tend to use phi of x, which is then equal to the probability that this random variable z is less than x, which is equal to the integral from -infinity to x of my probability density function. I'll tell you what, I'll use z's here, it's a little bit cleaner. So phi of z, for capital Z less little z, integral from -infinity to z, e to the minus x squared divided by 2, 1 over square root of 2 pi dx. Okay, right, and like we noted before, so just from the picture that we saw here, notice it's nice and symmetric. Okay, so the amount of probability to the left of say 2 is equal to the amount of probability to the right of -2. Right, so note by symmetry phi of z is equal to phi of minus z, right? That's for all z belong to the real numbers. Okay? Right. We can slightly generalize the normal distribution. Okay? So we have considered a standard normal distribution. Okay, so basically the point of this is, and I'll just move this down a scooch, is that we can allow the mean and variance of a normal distribution to take other values. Okay, so remember I was saying, for example, height is modelled by a normal distribution. Well, a standard normal distribution, which has a mean of 0 and a variance of 1, doesn't sound like a very good model of our height. Okay, so we need to maybe be able to change the mean, okay, and also kind of the units by changing the shift, the sort of the spread of the distribution as well through changing the variance. Okay, so so for x, well, let's say a normal distribution with mean now of mu and standard deviation, or I'll tell you what, just let's say variance and variance sigma squared. So here sigma is the standard deviation and sigma squared is the variance, has probability density function, okay, given by p of x, which is equal to 1 minus square root of 2 pi sigma squared, all square rooted, e to the minus x minus mu divided by 2 sigma squared. Okay, and that's again is for values of x belonging to the real numbers. Okay, so really one thing I can say, let's explain this in a second. Okay, so so if x is normally distributed, let's say just normally distributed with mean mu and variance sigma, then we write x is related to a normal distribution, and rather than having a 0 here, because the mean was 0 previously, we put mu, and rather than putting 1 here, sorry, there should be squared there, we'll put sigma squared. Okay, so sort of what's the difference between a normal distribution and a standard normal distribution? So we can say that, well, they're kind of connected as follows. If x is normally distributed with parameter mu and sigma squared, then I can get to a standard normal distribution by taking x, sort of deducting the mean of it. Notice if I take the random variable x and its mean is equal to mu, then the mean of x minus mu is going to be 0. All right? Also notice with the variance, okay, if I take a random variable here and I divide it by sigma, okay, then the variance is going to be reduced by a factor of sigma squared. Okay, so then we go from a random variable that's normal with a mean mu and sigma to a random variable that's going to have a mean 0 and a variance that's equal to 1. Okay, so then this is going to be normally distributed with mean 0 and variance equal to 1. Okay, in fact, quite a lot of the time, a lot of the kind of calculations that you end up doing with normal distributions is converting them into standard normal distributions, and then there are lots of standard software packages and tables and things like this for doing calculations for standard normal distributions. Okay, so we can note that we can sort of move between one way of calculating things and the other as follows. So notice, if we look at, say, x as a standard normal distribution, well, we're interested in the probability that normal distribution, not necessarily a standard one, but just a normal distribution here, is between a value of a and b. Okay. All right. So just as before, I was calculating the probabilities between b and some interval. Okay. Well, what I can do is I can just do the same arrangement that I did here. Okay. So notice I can minus mu off both sides of this expression. Okay. And the event stays exactly the same, because let's say if this is if we're considering the set of outcomes where this is true, well, that's exactly the same as the set of outcomes where this is true, and vice versa. Okay. Similarly, if I divide by sigma, okay, then the same is true. Right. So then what I have in here is a standard normal distribution, z. Okay. So then I can apply my rule that this is equal to the probability that z is less than or equal to b minus mu divided by sigma, minus the probability that z is less than or equal to a minus mu divided by sigma. Okay. Remember that this event plus this event gives me that event. Right? So I can use my probability rules from before. Okay. So this is just saying that I've got probability of A for this event plus the probability of B, where B is this event, was equal to the probability of A union B, okay, which is just this event. And notice these are disjoint. All right? Okay. Now, so okay, that kind of covers most of the things that I wanted to cover about just the definitions of the normal distribution. In a slightly separate video, I'm going to cover exactly why this distribution, the normal distribution, is of so much interest. Okay. All right, so we're going to do that in a second. All right.